Hello everybody, my name is Dhruv Sandesara and I study at Cinco Ranch High School. I love physics, I spend a lot of time on it and it is my passion, and today I'm shooting a video for optics which I feel people find difficult to understand and difficult to comprehend. I'm shooting this just with my iPhone and a torchlight beaming in my eyes. So just let's get to the nitty gritty of it. I want to start out by saying in optics, light, according to physicists, has a constant speed in vacuum, and that's the maximum speed it could go at, which is 3 times 10 to the 8 meters per second. But the speed of light does change in different mediums like glass and all that different matter, which permit light through it and are not opaque. So, and thus the ratio of the speed of light in vacuum over the speed in that medium is what we call as refractive index, and all of the time refractive index is greater than 1 because light travels fastest in vacuum and slower in other mediums. And when the one thing that physicists have observed is that light bends towards the normal when it's going from a rarer medium, which is air or vacuum, to a denser medium, for example glass. Over here we will see how this happens. We see the light bending towards the normal, and the angle of incidence is I, and the angle of the refracted ray and between the normal is angle R. And also the refractive index of an object is sine of angle I over sine of angle R. And this is also helpful in the cases when you don't know the speed of actual light in that medium, but rather the angle at which it strikes. And you could use this to find refractive index. So now we know that when it goes from air to glass or any other optically dense material, light bends towards the normal, and when it emerges from that or that medium back to the first one, which is the rarer one, it bends away from the normal. And when we use a rectangular block, the incident ray and the emerging ray are parallel but have a distance, which is the lateral displacement, how much the light beam has been not deflected, but shifted from its original path. And this depends on the refractive index, because that's the amount the angle is changing, and also the thickness, because that's how much it would change. When we look at prisms, the emerging surfaces are at an angle, so we can use a prism for making the light deviate a very huge amount, because when it goes from the rarer to denser, it will bend towards the normal, which will be downwards in this case. Let me show you the picture first. This one. So this is the emerging incident ray, the refractor ray, and the emerging ray, and we see at first it goes towards the normal. Over here now you have a different normal, and over here as it goes back into air, it goes away from the normal, and thus we see a major deviation in the path of light. Most of the pictures that we see are about polychromatic light, which shows how white light splits into its original component, the Vibgyor, violet, indigo, blue, etc. But over here we are gonna examine monochromatic light, which is only one color, so we know it takes one path rather than splitting up into its components. We could take the reason why the polychromatic light emerges is because all the lights have different speeds in that medium, and what we need to keep into account is that the frequency always depends on the source, so it does not change except in more complex situations such as the Doppler effect for light. In this case, no, the frequency does not change. As a light wave slows down, the wavelength of it, the frequency is constant. How long the wave is, the wavelength will change, and if the speed decreases, the wavelength will decrease. So we're done with that. Now I'll try to focus more on the lenses part, and there are a lot of type of lenses. These are the ones I'm talking about. Biconvex, which has convex on both the side, plano-convex with one plane side, and convex, and a lot more. We will be focusing on the biconvex and the concave lenses. Keep in mind that when we have mirrors, they will be coated on one side, so the light ray would not emerge in this side, the major component of it, but it would be reflected back to the same side from where it came into, while in the concave case it would still go back to where it came from. This is what we mean by the mirrors. And these are the lenses. So while lenses, we need to consider three things. That lenses are made from polished sides of two sides of a glass piece so that it can refract the rays, as we learned earlier. Their surfaces, they're the edges of two imaginary spheres of which they're part of. And first let's look at a convex lens. Just a second. A convex lens is a converging lens. It makes the beams which are going from one side meet together at a certain point in special cases. First, we need to establish these three things. The lens is just a combination of rectangular blocks and prisms. As you can see, the top part acts like a prism, and thus the ray going through it at a straight angle would go back through the focal point. The focal point has a distance of f that is halfway from the center of curvature, which is the center point of the imaginary spheres we talked about, and thus 2f is the radius of the whole imaginary sphere. So as we go from infinity, we see two parallel waves going through the lens, and then they meet at the focal point. Also, as the middle point is a rectangle, or we assume that in common terms, the light will go undeviated from that point, and thus we will see a straight thing. Also, when light passes through focal length, it would be the opposite of the first case. Now we would have a parallel beam, and we just use all of these three to find how the rays would end up. And thus, when we have a point at infinity, the image forms at focal point. When we have beyond 2f, it forms between the focal point and 2f. When at 2f, both the images are of the same size, and at 2f, one on the left, one on the right. Remember that we're talking about convex lenses, not concave. Concave is different. And between 2f and f, the object, we have an image beyond 2f. So now we go, first we had diminished images and very small point images. Now we have enlarged images. Till 2f we have same size. from when we go from 2F to F, we see a magnification of images. I will be using the physicsclassroom.com module to show this. So right now, the first ray that we see is the parallel one. You see how it's going parallel, then it goes to the focal point. The second that we consider is going through the focal point, which gives us a parallel ray. So as we're considering the top of the candle, the place where they will meet is where the candle forms as an image, and the top of the candle forms, and thus we make this thing our image. Remember, in this case, the image is actually formed and could be caught on a screen. Thus, we have a space, an image, which is called a real image, which is not virtual or any trick of the brain or eye, that we feel that the rays are coming from that point. And the third ray that we use is through the center of the lens, which goes undeviated for very, very thin lenses. When we go till infinity, we see the image is very short and approaching F or very diminished. When we go, or this is also beyond 2F, when we go till 2F, we see equal size of objects. When we go between 2F and F, we see magnified, and till F, we see the rays become parallel and no image is formed, or a really, really huge image is formed in our case. When we go between the central point and the F, we see virtual images to be formed. In this case, the light rays that emerge never meet. Thus, when we keep an eye on this space, it appears to us, when we put the eyes in this case, we feel as if these two rays are emerging from this spot. So that's where the candle is what our eye feels, and thus this is a virtual image, as there are no actual meeting